Richard here again. So now we're moving on to Lecture 7, Modern Methods for Shrinkage and Penalisation. Today's lectures so far have really introduced the idea that we need to validate our model, and in particular we're concerned about the fact that our model's performance may be optimistic and unstable, and that we need to examine that and potentially adjust for it. And the sample size lecture has reinforced this by saying let's make sure our sample size is large enough to minimise the potential for overfitting. Well, we are now going to think about some what are called more modern methods for dealing with optimism during the development process, called Lasso, elastic net and ridge regression methods. I'm going to introduce some examples, but then also really hammer home the limitations of these methods and the importance still of having a large enough sample size. So part 1, going beyond the uniform shrinkage factor. So the shrinkage approach that we've introduced so far has been what we've called a uniform or a global shrinkage. And this is where, after we've fitted the model, all the beta coefficients are shrunk by our uniform shrinkage factor as estimated by bootstrapping or the heuristic shrinkage factor. So for example, we have this equation, this logistic regression equation with our predictor coefficients, predictor effects, and these beta terms here post estimation were multiplied by S, our shrinkage factor, which was obtained by bootstrapping or by a closed form approach such as a heuristic shrinkage. And we emphasize that this is a general thing that we can do with any regression model, with a linear, logistic or Cox regression, where given our linear predictor, the betas in there, we can multiply them by S and re-estimate the intercept to ensure calibration in the large. But there are other penalisation approaches that actually act during the model estimation process itself. You may have heard of them: ridge regression, Lasso, which is least absolute shrinkage and selection operator, and elastic net. Now these methods modify the underlying statistical likelihood that's behind maximum likelihood estimation of logistic regression or Cox regression or linear regression. They adapt that likelihood by adding a penalty term, and this penalty term, it basically ensures that shrinkage occurs. Note that although you don't notice this in actual software because this happens behind the scenes, when we add in the penalty terms, the way the approach handles this is to make sure that all predictors are centered and indeed standardized, so divided by their variances, so they're all on a common scale, so that the penalty terms act in a common way on that particular scale, but then they are back transformed afterwards, so you don't actually notice it in the process itself. So there's a standardization of the predictors behind the scenes during the estimation, and then they come back transformed afterwards. The key thing is that these penalty terms allow for shrinkage during the model estimation itself, whereas a uniform shrinkage was a post-estimation task. Now, these models are actually all part of the same family, which we'll come on to in a minute. But in brief, ridge regression is allowing, through the penalty term, predictor effects to be shrunk towards zero, a bit like the uniform shrinkage factor approach, but it will never shrink them all the way to zero unless every single predictor effect is shrunk to zero. The key thing though is that unlike uniform shrinkage, which shrinks all the predictor effects by the same amount, the ridge regression approach allows different amounts of shrinkage per predictor. So if you've got a very uncertain predictor with a lot of noise for that particular predictor, then it's likely to get shrunk more than another predictor which has a lot more information about it. Now, Lasso and elastic net also have that same property where they can shrink different terms by different amounts. However, they also allow a subset of predictor effects to be shrunk all the way to zero. Now that is exciting because that means that they allow variable selection. essentially they allow variable selection and penalization to occur together. So the variable selection is through the shrinkage, and it therefore is also potentially more desirable compared to backward selection, especially if you've got small numbers of events per variable. So backward selection with followed by uniform shrinkage identified from bootstrapping might work well, but in smaller samples it probably doesn't work as well as when it does in larger samples. And the lasso is clearly a more sophisticated and complete approach to do all this in one go, rather than doing backward selection followed by bootstrapping and then uniform shrinkage. What is even more exciting, some might say, is that these methods allow us to develop prediction models even when you got very large numbers of predictors compared to the sample size. So even when you've got more predictors than events. Now, statistically, that is something that's always been a bit of a puzzle and doesn't seem to fit well. But these methods, because of the shrinkage and the penalization, they allow for that. So in high dimensional data, where people are fitting prediction models with thousands and thousands of variables and hundreds and 100 or 200 events, even less than that, these models will work and fit. Well, when I say work, I mean they will fit. Whether they work or not, I'll come back onto in a minute. Okay, so I've mentioned the penalty terms, so let's have a look at that in a bit more detail. The penalty terms for lasso and ridge are sometimes called L1 and L2 penalty terms, just so you know, because you might hear that terminology when you listen to talks or read things elsewhere. They're also known as tuning parameters, so the parameters within the penalty term are known as tuning parameters. The lasso, ridge and elastic net are actually part of the same family. We can write it as this expression here. So we have a likelihood function that's based on our standard regression, linear logistic Cox regression, for example, and then we add the penalty term to the likelihood, which is this lambda, so that's one parameter, and then we have inside the bracket another parameter alpha, and we've got 1 minus alpha over 2 times by the sum across all predictor parameters of the predictor parameter beta squared plus alpha times by the sum from 1 to p of the modulus of the predictor parameter. Now, like I said, alpha and lambda are the two parameters that define this penalty term. Now, ridge is when alpha equals 0, so this part of the equation disappears. Lasso is when alpha equals 1, so this part of the penalty term disappears. And elastic net is a hybrid between the two, and the hybrid is defined by the alpha term. So depending on the alpha depends on how much weight is given to the lasso or to the ridge. If lambda is equal to 0, we revert back to the original unpenalized likelihood. Okay, so if lambda is 0, there's no penalty term added, and we revert back to the original likelihood. How do we estimate lambda? Well, typically this is using the data at hand and estimated via cross-validation. Similarly for alpha, although sometimes we may just say 0.5 if we were using elastic net. Of course, alpha is defined by 0 and 1 if we're doing ridge or lasso, but elastic net we would have to estimate it or predefine maybe 0.5. So we're talking about using packages such as glmnet in R or elastic regress in Stata. Other packages are available. Okay, so we've added a penalty term into our likelihood, and that's going to introduce bias deliberately into our estimates, but the gain is that through the shrinkage it's going to potentially improve the mean square error of our predictions. We can also think about the use of penalty terms in the likelihood as essentially a Bayesian approach, where the likelihood is being modified with prior information. So a Bayesian approach incorporates prior information alongside the likelihood, and here we can think about prior distributions that are being added to be combined with the likelihood that lead to shrinkage towards the null. Either way, whether we think about it as a Bayesian analysis with particular prior distributions, or as a statistical likelihood that's had a penalty term added, what we're doing is we're adding in extra information that leads to biased predictor effect estimates to reduce variability of outcome predictions in new data. Now, there is more detail that can be gone into in terms of the likelihood and all that entails, but I don't want to get bogged down in that in this lecture, because I want this to be a very practical discussion and focus on the course. If you want more details, there's a very nice introductory video by Derek Kane here, and of course the original papers by Tib Shirani and Zhu and Hasty are worth a read if you're got a statistical hat on, shall we say. Okay, let's now think about the fact that we've got in our armory uniform shrinkage, we've got elastic net, lasso, and ridge regression, all these approaches which are all aiming to do the same thing. So which is best? When the events per variable is not small, and I say that loosely, so based on that original 10 EPV rule, then the choice of shrinkage method does not seem to make that much difference. The key thing is to use some penalization method, and that's been the message on the course so far. Make sure we do some penalization method. So here's a paper by Ewak Starberg and colleagues comparing different penalization methods, and in their particular data set they found no major differences between application of a linear shrinkage factor, a penalized maximum likelihood procedure, or the lasso. Okay, so linear shrinkage factor is just our uniform shrinkage. And this is in settings where the events per variable is decent, so the sample size is reasonably okay. However, other people have looked in settings where the events per variable is small, so let's say less than 10, maybe 5 or less than that per events per variable. And here's a paper by Pavlo and colleagues. Ridge regression performed well, except in scenarios with many noise predictors. Lasso performed better than Ridge in scenarios with many noise predictors and worse in the presence of correlated predictors. Elastic net performed well in all scenarios. Okay, so in small sample sizes, these methods start to come into their own. Similarly, if we compare sort of backwards selection, typical backwards variable selection with these novel, more modern approaches, we see that these modern approaches do better. So here's a paper by Martin van Smeden and colleagues. In smaller samples, backwards elimination with p less than 0.05 or the AIC criteria, so like p less than 0.157, generally performed worse than an equivalent regression without predicted selection or using the lasso. Okay, so just putting in the model with the predictors included does better than backwards selection, and using a model with using the lasso technique for estimation does better as well than compared to backwards selection. Notice that's not comparing it to backwards selection with uniform shrinkage followed by that. Okay, so it's not quite as we would compare it. Right, so clearly Lasso, Elastic Net, they're all showing promise, and indeed they're hugely popular. Many people see these as the gold standard and the solution to having too many predictor parameters compared to events. And indeed, this message has often been put across. So here's a paper, how to develop a more accurate risk prediction model when there are few events. So these penalization methods are very important, but are they as foolproof as perhaps some people are making out? Let's look at an example. Going back to the Gusto data that's been used in the practical, 30-day mortality risk, we've got 7 predictors, about 2,200 participants and 135 events. We've got 20 events per variable, so it's very big. Not done a formal sample size calculation here, but clearly that's going to be at least reasonably very good. The heuristic shrinkage factor estimated post-estimation of fitting this model was 0.97, so clearly the overfitting is very small. just about 3% overfitting. Let's have a look to see how Lasso does compared to the original approach that we've used of just forcing in all the predictors. So these are our 7 predictors plus the intercept term going in here. So this is our original model. We just fit a logistic regression. If we fitted a heuristic shrinkage following our unpenalized standard maximum likelihood estimation, we apply that 0.97 to these beta effects, and we get some very slight shrinkage, but not much. For example, 0.39 goes down to 0.38, and revise the intercept slightly. Let's try Lasso. So in Stata, for example, there's a package called LastPack, and we can use Lasso logit, and we can apply the Lasso regression to the coefficients. So the model is fitted, and at the same time the penalty term is in there, so we get penalization during model estimation, and we see that the Lasso estimates are very, very similar, aren't they, really? Minus 0.23, minus 0.20, 0.38, 0.36, 0.01, 0.01, 1.55, 1.56, etc. So whether we've used a heuristic shrinkage, which applies the same shrinkage factor to all the betas, or whether we've used the Lasso approach, we get very, very similar results. This is in a setting where EPV is very, very big. So that's reassuring, isn't it, that when the EPV is large, we're not likely to get too much difference. Now let's add in 50 noise variables. So 50 variables that are not predictors are just randomly put in, and some of them potentially could get picked up by chance. So I'm going to label those V1 to V50. They're all continuous variables. So now rather than 7 predictors, I've got 57 predictors. I remember again 135 events, so we've got about 2.5 events per predictor. So this was my original model, which just had the 7 predictors. Let's now fit my original model predictors, 7 predictors plus the 50 others, and force them all in. If I do that, then my heuristic shrinkage is now 0.8. Okay, so that's quite large overfitting. Start to be a bit worried about the amount of overfitting there. So is this a situation where the Lasso, for example, might really help us? I think it is. We could apply heuristic shrinkage again, so we could apply the shrinkage factor of 0.8 to all these regression coefficients, but clearly what we'd like to do is get rid of some of these coefficients, these predictors, because we've got 50 in there, and we'd like to get rid of some because we don't really want that complicated a model to use in practice. What's happening here is we're essentially in a situation where we're not quite sure what is prognostic, what factors are prognostic or not, and we're sort of amalgamating prognostic factor research with prediction model development, and that leads to a lot of sort of uncertainty and a lot of sort of back and forth about what should be included. Okay, so we could do a shrinkage factor to all the 50, but Lasso would allow us to select as well. So let's try doing Lasso with 57 variables, and what happens? Well, we see that it's selected, it hasn't selected HTN, but it has selected the other 6 of the main variables that we know are important. And it's also only selected 2 of the other 50 noise variables. So it's selected V7 and V21, but none of the other 48. So that is showcasing the real strength and promise of the approach, isn't it? We've got a situation of 57 variables, lots of noise. It selected 6 of the 7 that are actually important, and only 2 of the ones that are not. So that's really sort of a selling point. However, what are the downsides? Well, one downside is it hasn't got HTN in. It's shrunk that all the way to 0. All the other variables are also heavily discounted. So sex, if we just did the original model, was 0.39, the predictor effect. Now it's shrunk down to 0.08. Similarly, HYP, 1.6, now down to 1.07. 0.22 for ISTE, down to 0.11. So the consequence of you adding in a lot of variables and having too small a sample size is discounting and more shrinkage. And yes, therefore it reduces the problem of all these predictors, but at the expense of losing a lot of the prognostic information that is actually would have been there for these other variables if we'd just been focusing on these in advance. So this is what this slide summarizes. The standard approach gave us 57 variables in the final model. The Lasso approach gives 8 variables in the final model. So it's a really great example of why it's attractive. But the consequence is it got rid of HTN, which is an important predictor. There are other predictors that remained that generally are important, but they were heavily discounted, reduced effect sizes. 2 variables were entered by chance when they weren't actually important. And clearly, because the predictor effects are shrunk so far down, your Lasso model is going to have a worse performance than the standard model if you'd actually predefined just those 7 predictors. Okay, so there's some positives and also some notes of caution. I want to just focus a bit more on these notes of caution, and in part 3 look at issues with penalisation methods. So why worry about overfitting? Like I said, penalisation and shrinkage methods are hugely popular and indeed generally seem to work well on average. Sometimes over-predict slightly, so over-shrink on average slightly. But generally, on average, they're expected to do quite well. An issue, though, is that in prediction models development situations, we're not thinking about on average, not thinking about on average across all models that we develop. We want to make sure that the model we develop is reliable. So what are the concerns? Firstly, that tuning parameters are going to be estimated with large uncertainty and that your final model predictors are not stable. So if you repeated your study again, would you get the same lambda? Would you get the same set of final predictors? The lower your sample size, the worse this instability is going to be. Even when we apply uniform shrinkage, using the methods we introduced earlier in the day, your value of S is still just an estimate. So the value of uniform shrinkage that we apply, we don't know if it's right. It's our best guess. And in small sample sizes, there's going to be a lot more uncertainty about it. So actually, sadly, when we need it most, shrinkage and penalisation is more likely to fail us because the uncertainty on our estimates of lambda and S are going to be so big when the sample size gets small that we have less reliability that it's going to work. Now these concerns led to Van Houwelingen in 2001, so 20 years ago, to highlight that shrinkage works on the average but may fail in a particularly unique problem on which the statistician is working. And he observed that it's surprising that the estimated shrinkage factors can be quite off the mark and are negatively correlated with optimal shrinkage factor. So by that last statement, he means that if by chance you happen to estimate a very large R squared, then you'll estimate that you don't need as much shrinkage when actually you potentially do if that large R squared is just a completely chance finding. So ironically, in those situations where overfitting is of most concern, you're going to struggle the most to get it right. And the following slides just give some examples that illustrate this, taken from a recent paper that we published in the Journal of Clinical Epidemiology. In this first example, I'm going to consider a very simple situation of a linear regression, so a continuous outcome, 7 predictors in my model, and the R-squared of the model is about 50%, so it's a pretty good model. But what shrinkage is needed after I use between 20 to 253 participants in my model development? So 20 to about 253 subjects in my model development, and I'm plotting here the estimate of the uniform shrinkage factor obtained from bootstrapping after I've fitted my model. So down around 20, where you've got about 3 subjects per predictor, the estimate of the uniform shrinkage is around about 0.7? But the 95% confidence interval for the true shrinkage estimate is between about 0.2 and about 1.1. So we really have so much uncertainty about what the best shrinkage factor to use is. Obviously, as we increase the number of subjects, the uniform shrinkage factor estimate gets closer and closer to 1. And we see around about 100 participants that we get a shrinkage factor of 0.9, and it's only around here that the uncertainty around the estimate starts to get reasonably narrow. So as the number of subjects increases, our shrinkage gets closer to 1, so the shrinkage required is less and less, and the uncertainty is reduced. But down this far end, when sample sizes are low, we've got a lot of uncertainty about how best to apply shrinkage. What about the other methods, such as elastic net and lasso and these other approaches? Do they do better? Well, this is a simulation study that we present in our paper, where we developed our model for a binary outcome, so a logistic regression situation. We had 20 predictors. The outcome instance was about 50%, and we looked at situations of 100, 200, up to 500 sample size. So up here, the number of events is about 250, and there's well over 10 events per variable in this particular setting. Down here, we've got about 5 events per variable, so quite small. When we look at developing models using simulation and then testing it on a very large data to see the truth, we see a quite scary picture. So when we test the calibration slope in new data, if we use standard maximum likelihood estimation, we get badly wrong. The calibration slope is woefully less than 1 because we're not doing any shrinkage or penalisation at all. If we apply uniform shrinkage through bootstrapping, the green, or heuristic shrinkage, this one here, we see that we do a lot better, we get closer on average, but there's a lot of uncertainty. Bootstrap has less uncertainty. That's interesting to see, indicating why we prefer bootstrapping. But Lasso, elastic net and ridge regression, they don't really do much better either. In fact, they overshrink, so the calibration slope in new data is actually bigger than 1, and there's so much uncertainty about the calibration slope. As we get larger sample sizes, we see that the middle, the black lines in each of these, gets closer and closer to the true ideal value of 1. And crucially, the uncertainty around your estimates also is reduced. So, for example, at 500, the uncertainty about the bootstrap estimate there is reasonably small, although still, not unsubstantial, going from about 0.7 up to about 1.5. So even with decent sample sizes, we're getting a lot of uncertainty, and this just reflects the instability, and that the Lasso and these modern methods, they don't solve it. They don't solve problems of low sample size. So for example, you could develop a model in a sample size of 100 participants here, about 5 events per variable, and use Lasso and think you're fine. Well, you're not. In new data, the calibration slope might be up to 5, might be actually down to about 0. On average, you might do quite well, but on average is meaningless when actually you're just focusing on one particular model that you're developing using the dataset at hand. So we need decent sample sizes to reduce our uncertainty and to improve the stability in new data, and that's the key. This has also been found recently by a paper by Ben van Kelster and colleagues, and again, similar conclusion. The results imply that shrinkage methods do not solve problems associated with small sample size or low number of events per variable. So this is a common message that's now coming across, people pushing back against these modern penalisation methods. And lastly, let's go back to our real example that we've used throughout the course in primary biliary cirrhosis. Remember, 6 predictors, we had about 15 events per variable, so we don't expect too much overfitting, and we didn't see too much overfitting. The calibration slope was about 0.911, so there is overfitting and it needs to be adjusted for, but it's not seemingly enormous. But let's have a look at the uncertainty. What is the correct estimate of our uniform shrinkage that should be applied? Well, the uncertainty and the optimism from my bootstrap samples is between minus 0.133 to 0.311. So my best estimate is that the optimism in the calibration slope is 0.089, but actually it could be anywhere between here. So translating that back to the shrinkage factor, this gives a 95% confidence for the shrinkage factor of between 0.689 to 1.133. Okay, so that's 1, the calibration slope, minus 0.133, that gives us 1.133, and 1 minus 0.311 gives us 0.69. So our best estimate of the shrinkage is 0.911, and we're 95% confident it's between about 0.7 and 1.1. So again, it's not ridiculously narrow. There's definitely a lot of uncertainty, even in a situation where we've got 15 events per variable. So my point to you would be, should we even be thinking about developing models when the sample size is too small? I would say absolutely not. So we prefer to develop models using large sample sizes. So make sure you've got your sample size right. That's first and foremost. Suitable events per predicted parameter. You should be aiming to minimize overfitting, ensure precise estimates of your parameters, at least the intercepts. Aim for a stable model, and I think you're more likely to do that when you're building on existing evidence. So you know in advance what predictors are going to be put in your model because you know that they are prognostic factors based maybe on systematic reviews, previous evidence that's shown they're prognostic. And then, we quite happy to apply, in the situation of decent sample size, a uniform shrinkage factor post-estimation to deal with any overfitting. When I say deal with any overfitting, I mean the best estimate to address overfitting and optimism. I've already shown you that even in situations with decent sample size, you may not get the right estimate because of the uncertainty that remains even then. If you've got a situation where your sample size is not big enough for the number of predictors you want to consider, then you need to reduce the number of predictors. And you need to do that before model development. So, like I said, what models, what studies are out there that tell us what predictors are important? Let's use and focus on those. If we need to reduce and we don't have any of the previous evidence, then we could think about looking at the correlation amongst the predictors and maybe getting rid of some that are highly correlated with each other, focusing on those that are most easily and affordably measured. Principal components analysis may help us to identify the predictors that are least correlated with others that might be important to consider. So there's a process that can be gone through before we suddenly jump in and say, oh, let's throw in 1,000 predictors even though we've got 100 events. That's not something we recommend. If we want to do variable selection using some statistical approach during the model development, then we again are happy to use backward selection followed by uniform shrinkage, where the uniform shrinkage estimate is from bootstrapping and allows for backward selection during the bootstrapping process, so it's honest in terms of that process of variable selection. We're also happy to use a lasso or elastic net for variable selection in situations where the sample size is appropriate, because it's those situations where the sample size is appropriate, the backward selection and the lasso or elastic net are going to be stable or more stable. If the number of predictors is large and the events are few and key predictors are unknown, then this is a mess and it's unlikely that you're going to develop a reliable model in this situation. Lasso, elastic net are very alluring and attractive in this situation, and they'll allow you to develop a model, but don't be fooled. There's no free lunch here, and instability will win the day in nearly all situations. For example, you may find that important predictors are lost. The effects of important predictors may be diluted even though they're retained. You may end up with predictors that are included that are just noise variables and shouldn't be there, and the model therefore is unlikely to validate well in new data. In this situation of large number of predicted parameters, few events, another big option is don't even develop a model in the first place. Rather concentrate on identifying what factors are prognostic. Use your data set to look at prognostic factors and investigate prognostic factors and whether they add value over existing factors. I think a lot of the problems in our field are people jumping in to develop their own prediction model when we really don't have enough evidence about what prognostic factors are there in the first place. So we're almost missing out the progress type 2 research and jumping straight into type 3.
Many of the things that I've been talking about in this lecture have a basis about stability. So Stability is such an important concept, but really not thought about much in detail by most people when they're developing a prediction model. Gary and I have published this paper in the Biometrical Journal, Stability of Clinical Prediction Models Developed Using Statistical Machine Learning Methods. And we talk about how to examine stability once you've developed a model, because it really is important to help expose concerns of quality and whether it's likely to be reliable in practice. So let's just have a little bit of a look at this. So we can quantify instability using bootstrapping. If you always go back far enough, you'll always see that Doug Altman did this first. And back in 1989, he looked at using bootstrapping to examine instability, and in particular to look at the variability in individual predictions. This is really important because if your bootstrap process to examine instability shows huge variability in individual level predictions, then it's telling you that the model is not stable. So that a different model from a data set of the same size with the model developed using the same development process that you did before, if that's giving you a very different prediction for an individual than your original model, then something's concerning. So the bootstrap process is basically you generate, let's say, 1,000 bootstrap samples, each of the same size as the original data set. Then in the bootstrap sample, you develop your new bootstrap model using exactly the same model development steps as you did to develop the original model. And that therefore produces about 1,000 bootstrap models. Then in the original sample, you apply each of those 1,000 bootstrap models. So you get 1,000 predicted values, estimated risks, for each individual in the original sample. So that means you've got an original model prediction and 1,000 bootstrap model predictions for every individual. And so we can plot a prediction instability plot. This is the bootstrap model predictions on the y-axis versus the individual's original model predictions on the x-axis, and we can do that for every single individual. We can also look at other instability. So what's the instability in the calibration curve? What's the instability in the MAPE, the mean absolute difference between the original and the bootstrap model predictions? So let's just have a look at some examples, because it's much easier to understand this with real examples. So I'm going to use a dataset called the Gusto-1 dataset, and I'm going to use it to develop a prediction model for risk of death by 30 days after acute myocardial infarction. Now this is a massive dataset, 40,000 individuals, about 3,000 deaths, overall risk about 7%. We are just going to use 7 predictors listed here. And for reference, if you fitted a logistic regression model in this data with these 7 predictors, the C-statistic would be about 0.8. So some predictive value in these predictors. Now on the left, I've got my prediction instability plot for a unpenalized logistic regression in the full data set. And I've got my predicted risk on the y-axis from the bootstrap models against the predicted risk from the developed model on the x-axis. You can see that this is very, very narrow. The spread of values is very, very narrow. Yeah, so there is stability. So for an individual whose predicted risk was 0.4 from the original model, the range around that from the bootstrap models is, between about 0.45 to 0.35, probably a lot even less than that. But what happens when we reduce the sample size? So reducing the sample size now down to about 3 events per predictor. I'm going to take 300 random patients from that original data set. Look at the instability now. So this dashed line is a 95% interval. So now an individual who in the original model had a prediction of 0.4, now the bootstrap models, the prediction value could be up to about 0.8 or down to about 0.1. So there's now much more instability, and that's starting to be a big concern, isn't it? Because if you're making decisions based on somebody's risk, and actually we don't know if their true risk is 0.1 or 0.8, then we can't really be confident in using that model without further information about its validation performance in a validation data set. Now let's have a look at a situation with, again, it's a small data set, 752 participants, 53 deaths, but I'm going to look at the 7 predictors plus 20 noise variables, so 20 extra predictors were they're actually not predictive at all. And therefore I've got about 2 events per predictor now. So if I fit a standard logistic regression, again, there's nasty instability plot here, again, where I've got predictions that, for somebody that's got a original model prediction of 0.4, it goes down from about 0.1 to now over about 0.8. You could have to say, okay, let's use the lasso. Let's see if the lasso resolves this issue of instability. What happens? Well, it does resolve it a little bit. So the shrinkage from the lasso approach resolves some of the instability. So you can see the spread of values is not as big as before, but still it's not gone away, has it? We've got a predicted value of 0.4, and the original model still goes from about 0.1 to about 0.8. So it's come down a little bit compared to this, but there's still a lot of instability in this plot. So again, another example of where the lasso, it's appealing, but it's not resolving the issues of a small sample size. What about random forests? So this is a machine learning approach. We've not covered machine learning methods, but I just wanted to finish this lecture just by showing you that it doesn't resolve all the issues. So again, now a data set of 500 participants, 4 events per predictor, and so this is going back to my original 7 predictors in my data set. And this is the lasso model, not doing too bad, but still some instability there that's of a concern. If I did a random forest and just applied a default instator, which is going to fit 500 trees, then I've got quite a crazy situation. Somebody's got a predicted risk of 0.8 from the original model. From the bootstrap samples, it could be 1 or down to about 0. So clearly the random forest is very unstable when fitted using the default methods. If I was to fit the random forest using a more considered approach, for example, to only have 100 trees with a depth of 3, then I get a much more stable situation. Similar essentially to the amount to shrinkage that you get from a lasso, or even stronger shrinkage to that, as you can see on the left. So much more stability. So again, just reiterating that when you're fitting any method, it's very important to understand the tuning approach. And the instability checks expose a lot of the issues behind the scenes that you might not otherwise be able to see. Okay, so that's just a warning about checking stability to help you understand the quality of your model.
So in summary, I hope it's been quite a fascinating lecture for you. You will have heard of these modern methods such as the lasso and elastic net, and often they are seen as the solution to all our problems in this field, but they really are not. They are useful and have worth in situations sample size is appropriate. Similarly, uniform shrinkage has worth in that situation. They're all good methods to think about when the sample size is appropriate. Lasso and elastic net, of course, they're appealing because they allow both penalization and variable selection, but they are dangerous in high dimensional situations because they let you do something that you probably shouldn't be doing in the first place. If the sample size isn't right, shrinkage and tuning parameters are going to be hard to estimate, your imprecision is going to be worse when the shrinkage increases, and you may start losing predictors and losing diluting predictor effects that wouldn't be lost if you actually had a process beforehand to really identify key predictors based on previous evidence. This all raises again the importance of internal and external validation. So internal validation using, for example, bootstrapping, looking at the stability or the instability of your model development process and what's retained in the model. If there's a lot of instability, then it's basically shouting at you, look, this is unlikely to work in new data. And because of the way that people develop the models using these approaches, external validation is always crucial because, a lot of the models we just can't trust. So external validation, new data by independent researchers is going to be crucial, and that will be something that we'll come on to on day 3. Okay, thanks for listening, and I hope that's been useful.